Okay, gentlemen, as promised, I wanted to do a quick little summary on limits just to kind of give you guys maybe like a visual graphic organizer of how you can think when you're given a limit problem. So essentially, there's two kinds of limits that you got to worry about, at least for this test and in general. Two kinds. The first one would be limits at infinity. So you might have the limit as x approaches positive infinity of something. Well, I'm just going to say that limits at infinity, either positive or negative infinity. That's one general type. The other type is a limit as x approaches a particular number. X approaches 2, or the limit as x approaches like 2 from the left side, or something like that. So that's the first thing you want to do when you are given a limit problem is check what are we talking about. Are we talking a limit at infinity? That's talking about the end behavior. What's going to happen, out at the ends of the graph? Is it going to be leveling off at 0? Is it going to go down to negative infinity? Is it going to level off at a constant, like y equals 1? Those are the kind of things we're going to get there. These guys over here, the limit as x approaches 2, the limit as x approaches 2 from the left, generally they're going to be situations where you're going to get like 0 over 0, generally if it's just a particular limit. If you don't get 0 over 0, if you get an actual number, that's the limit. You're not going to get any of those on the test, though. A one-sided limit, if I give you any of those, that's going to be a situation where at that value of 2, there's going to be something funky going on. That thing that's funky is going to be a vertical asymptote. And what I'm going to be asking you is that curve going to be going up toward positive infinity, or is it going to be going down toward negative infinity as you approach x equals 2 from the left side? And so I want to give a few minutes on each of these types so you can know what the basic strategies are. So let's go over here with the limits at infinity. Most of these are rational functions, meaning there's going to be a function on top of another. So something like, the limit as x approaches infinity, positive infinity of 3x minus 5 over 4x minus 2. Excuse me. And every time you have a rational function, a function on top of a function, and it's a limit as x approaches infinity, you're going to do our divide through by the highest power of x thing. But that's the only time you divide through by the highest power of x in the denominator, is limits at infinity with rational functions, okay? Don't start doing, dividing through by the highest power of x on these limits where you've got an integer that you're heading toward, or a fraction that you're heading toward. So I'm not going to take you through the limit as x approaches infinity of 3x minus 5 or 4x minus 2. We did a bunch of those, but that's a major concept that you have to understand. The other types of these would be something like the limit, the limit as x approaches, say, negative infinity of, let's do, 3x minus 5 over the square root of 5x squared minus 2. And this is the situation, again, where you're going to divide through by the highest power of x in the denom, but this is that thing where the highest power of x in the denom is a square root of x squared, 5x squared in this case. So we'd be dividing through by the square root of x squared. So we would take this thing and say the limit as x approaches negative infinity of 3x minus 5, we're going to divide through by something. And then down at the bottom, you're going to divide through by something. Oops, that's a 5, not a 3. 5x squared minus 2. And in the denom, because we have this square root of x squared, we're just going to put an x squared down here and an x squared down there. And in the numerator, though, the thing that we wind up putting in here, under here, and under here, has to be exactly the same as this, which is the square root of x squared. So you say, okay, we need to put in the square root of x squared right there. But for negative values of x, which is what we're going to be looking at with x going toward negative infinity, the square root of x squared isn't x. It's the opposite of x. So you put in an opposite of x here and an opposite of x there. And then I think you should be able to find some examples in your notes where we reduce this thing. We're going to cancel that with that, and we're going to get -3, and we're going to say this limit, because we have an x in the denominator of some power and a constant in the top, is going to be 0, so plus 0. And in the bottom, these x squareds are going to cancel out, and you're going to get a root of 5. And again, a constant over a power of x is always 0. So you're just going to put, minus 0, I guess it is. It doesn't really matter because it's 0. And you get -3 over root 5, and that's your answer. But it's real important that you understand that when we're going toward negative values of x, for negative values of x, the square root of x squared is the opposite of x. So I would count on something like this guy being on there tomorrow. So there it is. Limits as x approach positive or negative infinity. You're just going to divide through the highest power of x and see what's happening. There are the types, I guess I should add that one more, where it might say something like the limit as x approaches, let's say positive infinity this time, of x squared minus 3 minus x, which is an indeterminate form of infinity minus infinity. We don't know what's going on there. So it may turn out to be 0, but it not necessarily will be 0. So what you're going to do there is, because you've got a radical thing, you're going to multiply by the conjugate, minus 3 plus x over itself, x squared minus 3 square rooted plus x. And sorry guys, I inadvertently hit the play button. So we were just saying this thing is going to wind up coming down here, and you're going to get the square root of x squared minus 3, minus x. So all of that would be, so we're going to, you'd be able to deal with that though, because you can just divide through by the square root of x squared here, and the square root of x squared there, and the square root of x squared there, and what's going to happen is the top's going to turn out to be 0, and the bottom's going to be like the square root of 1 minus 0 minus 0, or minus 1 rather, and plus 1, I'm sorry, because that's a plus there. So it's going to be 0 over 2, which is a perfectly fine limit of 0. And again, I'm sorry, I got all messy here. But that's the thing with limits at infinity. Check to see it's a limit at infinity, and then divide through by the highest power of x in the denom. If it's one of these conjugate guys, again, the key is that eventually you're going to wind up dividing through by the highest power of x. All right, so now I want to come over here and talk about these guys. I'm going to probably start a new page because this is a mess now. But we'll talk about the different kinds of problems that you can see with specific limits at a certain value. So for the rest of these things, we're not going to be dividing through by the highest power of x. Okay, so here we go. We're going to just wrap up our discussion on limits, the two types. Limits at infinity, we just went through that whole last slide of some different examples of that, and that's the technique is to always divide through by the highest power of x that's in the denominator, but you do it to every term. Now, limits at a particular value of x. Limit as x goes to 2, limit as x goes to 0, limit as x goes to -3, those kind of things. These are basically our 4 types of problems that we've done. I think it was back in 1.1 and 1.2 we were doing things like factoring and canceling, simplifying a complex fraction using a com denom, having a radical expression and using the multiplying by the conjugate over itself. Recently in 1.6 we started to introduce trig, and we had these two new limits, sine of x over x and 1 minus cosine of x over x, or versions of those. And then lastly, one-sided limits. I referenced that a little bit on the last slide. But maybe really quickly I'll do one quick example of each time. It might not take them all the way through to completion, but we could certainly talk about it, and then maybe you can practice them on your own or whatever. So a factor and cancel is going to be something really basic, like the limit as x approaches 3 of, I don't know, x minus 3 over x squared plus, no, I lied, x squared minus x minus 6. And of course, if you plug 3 in as it is, you're going to get 0 over 0. But once you factor this thing, you get an x minus 3 in the top, and you get an x minus 3 and an x plus 2 in the bottom. And cancel those guys, you get 1 over x plus 2. do direct substitution, put that 3 right in there for that, and you're going to get 1/5. So that's a really, really easy problem, but I can't tell you how many times kids will have a problem like this, and because they're just confused between the two types of problems, they'll start dividing through by the highest power of x on this stuff and getting poop. Yeah, don't do that. Just keep your head about you. Look, first thing you do is say, what's our limit as x is heading to? Is it infinity or is it a number? If it's a number, you ain't dividing through by the highest power of x. Okay, com-denom, complex fraction. What am I talking about there? Let me think of something like limit as x goes to 1 of 1 over x minus 1 over x minus 1. So again, direct substitution, you put a 1 in for these guys, and you're going to get 1 over 1, which is 1, minus 1, which is 0. Put a 1 in the bottom, you're going to get a 0. So you get 0, 0. So com-denom, complex fraction, get a com-denom up there, put those two things together, and then you're going to recognize that something's going to happen. You're going to get 1 over x minus x over x, which can be written as 1 minus x all over x. And in the bottom, we have x minus 1. Oops, x minus 1. And I hope you can see that, if you take that denom and realize that it's really like x minus 1 over 1, when you reciprocate this and multiply it by the numerator, you're going to have a 1 minus x in the top and an x minus 1 in the bottom. And no, they're not the exact same, but they are opposites of one another. So you can cancel those things out, leave yourself a negative 1, and you're going to wind up getting like negative 1 over x. Then, because you've canceled out the 1 minus x's and the x minus 1's, that's causing your 0 over 0. Once you cancel those out, like I said, I think you're going to get negative 1 over x. Plug the 1 in there for x, and you get negative 1 over 1. That's your limit, negative 1. Okay, radical conjugate problem. We're talking something like root of x plus 3 minus 3 over x minus 6, or something like that. I think this will work. Yeah, so and we'd be looking at a limit as x approaches 6. So again, direct substitution, you put a 6 in here, you put a 6 in there, you're going to wind up getting the square root of 9, which is 3, minus 3, which is 0, over 6 minus 6, which is 0. So you're going to multiply top and bottom by the conjugate of the radical expression. So root of x plus 3 over root of x plus 3 plus 3. And again, it's something I stressed in the last day of class before the test, is when you FOIL these two guys together, you're going to get x plus 3 minus 9, which, of course, turns out to be x minus 6. In the bottom, do not FOIL this stuff out and do x times this and x times the 3 and negative 6 times that and negative 6 times 3. Just leave it as x minus 6 and root of x plus 3, because you get to cancel those. Then you're left with 1 over that. Do direct substitution, put your 6 in there, and you're going to get 1 over the square root of 9, which is 3, plus the other 3, and you get 1/6. So, got that guy done. And then, with the trig ones, we just spent, a class period and a half doing a ton of these things. I would just recommend that you look at 1/6 and every single problem in that whole batch of limits, you should just try and see if you can get them. We did a whole bunch in class. I would just pick the scariest ones and see if you get them. But that's always looking for, can I find a sine of x over x, or sine of star over star, or can I find this thing in there somewhere? Now lastly, these one-sided limit guys probably only have maybe one, maybe two of these. It might show up as a true false or something like that. This would be something like the limit as x approaches, let's say 3, from the right side of x minus 4 over x minus 3. Now, I said earlier on the other page that if you got a one-sided limit here, I'm asking that for a reason, because I know this thing's going to explode at x equals 3. This thing's going to have a vertical asymptote. You got a 0 in the denominator that's not a 0 in the top. This thing is going to have a vertical asymptote. But the question becomes, is this guy going to at x equals 3, if we put our red wall of death in there, from the right side, is this guy going to be going up like that or down like that? Now the key to this problem is all you have to do is do a test value, but you have to do a test value in a smart way. So we do a little sign chart here, and we say, all right, x equals 3 is what's called a critical number of this function because it makes the denominator 0. But the other thing that's called a critical number of a function is what makes the numerator 0, because that's going to be an x-intercept. So we go to 4, where we're going to have an x-intercept, and we have 3, where we're going to have a vertical asymptote. So what we're talking about with this function is our graph, rather than looking like what I have here and here, what could happen is, let's see if I can erase that stuff. Yeah, nope. I can only erase the most recent stuff. Okay, but I could fix that curve to say, all right, if we had an x-intercept at 4, let's say that's 4 there, and this is 3 here, that curve is going to be doing something like this. It's kind of going to either head down toward negative infinity, hit this 4 here and go above, or it's going to be down here and it's going to hit that and go up like that. It's going to be crossing the x-axis at 4. So the reason I'm doing that is just to emphasize to you how important it is, if you're going to test a value to the right of 3, that we stay in this interval here, stay between the asymptote and the intercept. If there was another vertical asymptote here, you have to stay between the two asymptotes. Because what's going to happen is, when you test a value between 3 and 4, for example, 3.5, put 3.5 in here, and all that matters is that that numerator is going to be a negative quantity. You put 3.5 in the bottom, and it's 3.5 minus 3, that's going to be a positive quantity. And because you have a negative over positive, for every number in this interval down here, you're going to wind up getting a negative number, which means it must be this case where we're going down toward negative infinity. So the only work you would show on that is a little sign chart. If you want to draw a little graph like that, you could. But your answer is negative infinity. So that's kind of what we're going to do with that. So that should do it. We got all the different cases that could come up, and good luck with it tomorrow. But again, just keep your wits about you that these guys, limits at infinity, are dividing through by the highest power of x, and everything else at a particular value x, do not divide through by the highest power of x. It's going to be factor and cancel, com, denom, radical conjugate, trig, or a one-sided guy. That's all. Good night and good luck.